So our next topic in our geometry foundations is not so much like a new term that we have to discuss, but more of a concept and a way of doing things. And so what we're going to be working on is understanding how measurement and congruence works. So understanding measurement and congruence. And so one of those words I feel like should be kind of obvious to us what it means, but the other one might be new, and that's the word congruence, and it's going to play a huge role in just how we think about segments and measures of objects later on. So let us start with our first well, actually, not a term, but a postulate that we have to talk about. So first we need to talk about what a postulate is. So axiom and postulate are two words. They mean the same thing. Most of the time I'm going to use the word postulate, but what it is not just something in geometry, but really in all of mathematics. It's a rule that is accepted without proof. So we have to start somewhere. We have to start at a place where we, have this just assumption of things that are true, and we can't necessarily prove them to be true because they're so fundamental to what we're going to be doing that we just know that they are. And so that first axiom or postulate that we're going to talk about is called the ruler postulate. And it says that each point on a line corresponds to a coordinate on the real number line, and the distance between 2 points is the absolute value of the difference of their two coordinates. And so it's kind of a complicated way of saying, look, if I have a segment, what I could do is I could measure this thing. And so normally, if we go to measure something, what we would do is, we would take our ruler and we line it up here where, the 0 is at this point, and then I have a 1 and a 2 and so on up to, say this is 5 centimeters long or something. But in reality, what we can do is that we could measure this same object by taking our ruler and misaligning it. So if this is my 0 still, this is 1, and this is gonna be way off, but 2 and 3 and 4 and so on. And what we'd end up finding out is that, well, it actually has the same distance. This would end up being 7, no matter what we line it up with. So, when we have a number line, like this, what just means is that, like on a number line, there are infinitely many points. It's the same thing on a line or a segment that we're trying to measure. And so, just like there aren't just 5 numbers on this number line, there are infinitely many numbers that I haven't drawn in, like 0.5 is right here, and somewhere over here is 4/3 and so on. Even though I only have these 2 points labeled, there are infinitely many points in between, and they each correspond to a value on the number line, which allows us to actually find their distance then. And so how we'll normally write this is that we'll call these coordinates. And so this coordinate here would be something like x1, and this coordinate here would be something like x2. And so their distance would be the absolute value of the difference between these two coordinates. So in this case, I could either have done it this way, where I take 5 minus 0, and that gives us 5, or when I lined it up on this number line, I got 7 minus 2. Either way, the distance between these 2 points is 5. And no matter how we number them, they'll always end up that way. Even though there's infinitely many points in between these 2 points, we can say that the distance is 5 units or 5 centimeters or 5 inches, whatever we're measuring in. Our next postulate is the segment addition postulate. And what the segment addition postulate tells us is that if a point lies on a line segment, then the distance from one endpoint to that point, add the distance from that point to the other endpoint, is the same as the distance between the two endpoints. This is a really long way of saying another really obvious fact, which is that if I have a segment call it AB, and I have a point on here someplace, call it segment C, it'll be the case that the distance from A to C plus the distance from C to B will be the same as the distance from A to B. So I can actually write an equation. Now the question is, how do I actually call these things? So I can tell you what we're not going to do, and probably what you might assume to be the way we do this is that I would take segment AC, and if I add that to segment BC, what I will get is the length of segment AB. And this is not how we write things. So we'll circle this, okay? Because whenever I talk about segment AC here, what I'm really trying to say are the points. And so it doesn't make sense to add the points to some more points and get another set of points. I left that off. And so the way that we do this is a different notation, is that if I want to talk about the distance between 2 points, what I'll do is I will call this distance right here AC. Okay, this is the distance between, or the measure of, segment AC I refer to in this way. Okay, and so measure AC will actually be equal to a number. So like when we had in the previous discussion, when I said that that segment was a certain length, I can say that this segment is 5 units, for example. It does not make sense for me to say that a set of points equals 5. This just doesn't, I'm talking about a set of points. It's not a number of points. It's not a distance. It's just a set of points. And so the equation that I can write here is that AC plus BC, because these are numbers, these are values, will be equal to AB. That length will be the same. Okay? And so there's a big distinction here between these two notations, and it's subtle and it gets overlooked a lot, but it's an important distinction that this talks about measure, while these talk about the actual points, the actual structure themselves. Okay, so that's the end of that postulate. Nope, I want to get rid of that. And then I want to define one last thing, which is congruent segments. So we used this word before, congruent. What congruence means, well, in this case, is that 2 segments are congruent if they have the same length. And so congruence in general means that 2 things have a shared property which is the same. And so here's what we could say. If I have a segment, let's draw a segment here, and we'll call it AB. And I have another segment over here that I'll call CD. And let's say these 2 segments are the same length. So, like before, what I can say is that AB, the measure of AB, is equal to the measure of CD. Okay? I can say that these things are exactly equal because there's some value, there's some number, it's the actual length of them. However, if I want to talk about the segments, so now if I say segment AB and segment CD, if I want to say that they have the same measure, what I can say is that they are congruent to each other. Now I have a notation for this. It is that they are congruent, right? So this is an equals operator, or equal sign, and above it, this right here is called a twiddle. So not really important to know, but it's what it's called. And this tells me that these 2 segments have some shared attribute that's the same. In this case, it is that they have the same length. So this is equality. This is congruence. Congruence means, equality means that 2 things are exactly the same. And so if I were to say, let's use a different color down here. If I were to say that segment AB is equal to segment CD, what I am in fact saying is that these 2 segments are equal to each other. They have the exact same set of points. And that is not the case, right? What I can say, though, is that their measures are equal to each other, which makes the segments congruent. It seems like a small thing, and it seems very subtle, but this is an important concept, which is going to lead us into proof later on in some further discussions. And so there's a difference here between equality and congruence. Equality means exactly the same. Congruence means two things have a shared attribute that is the same.